Okay, let's get started. So we finished sections 12.1 and 12.2 yesterday, and that was all about the introduction of how to use these double integrals to compute volumes and such, right? And we're kind of thinking more along the lines of these integrals as sums rather than, say, the area underneath the curve or volumes, but they can be utilized to calculate those things. So today we're going to start trying to do different coordinate systems. So this brings us to 12.3, and we're going to talk about double integrals in polar form. So you might have touched on polar coordinates in Calc 2, and the idea now here is how can we kind of systematically find maybe the area of a region here that's in polar coordinates. So let's imagine we want to evaluate some double integral over some region R of f of x dA, where R is easily defined in polar coordinates. So maybe we have a region draw 2 here. Perhaps we have just a circle and it's everything inside this circle. So this will be our region R, and maybe it's a unit circle centered at the origin. So we have a y squared plus x squared is equal to 1. So that's the boundary there. Or maybe we have kind of an arc, something like this, where this is our region R, where maybe the inside is described by a y squared plus an x squared is equal to 1. But we have on the outside maybe an x squared plus y squared is equal to 4. Right? And it's cut off exactly on the x-axis. So these are pretty easily described by polar coordinates, but they're pretty bad in Cartesian. So if we wanted to use x and y, we would have to put a lot of work in. But in polar coordinates, these are relatively easy. So kind of how to describe our first circle here is we can say that R is the set of all points R in theta such that we have that r goes from 0 to 1, and theta goes from 0 to 2 pi. Right, so the radius goes out to 1 and starts at 0 and goes all the way out to 1. And we make that radius vector like this, right? And it goes all the way around. So we have 0 to 2 pi, as well as every point for every specific angle, r goes from 0 to 1. So it creates this solid circle here. For this object, the radius, remember it's always centered at the origin, it goes from 1 and it goes all the way out to 2, right? This is a circle of radius 2, the outer arc here, described by x squared plus y squared is equal to 4. Now the angle goes from 0 to pi. So we could say that R is the region of all points R and theta such that the radius goes from 1 to 2 and theta goes from 0 to pi. Okay. So these regions are examples of polar rectangles. All right, so you might be thinking to yourself, what is a polar rectangle? It doesn't look like what I think of as a rectangle, but notice the bounds here. The bounds on r and theta are both constants. That's exactly how we defined a rectangle in Cartesian coordinates, right? Where both x and y were bounded by constants, right? So we say that a polar rectangle takes the form of all points r and theta such that we have that the radius is bounded by a and b, some constants, and we have that theta is bounded by some constants as well, alpha and beta. So similar to the Cartesian rectangle, we will divide the domain into smaller rectangles. But in this case, they're polar rectangles. So before, specifically yesterday, when we were doing these double integrals over rectangles in the Cartesian sense, we subdivided into sub-rectangles and then tried to estimate the volume or whatever the integral is doing in that specific sub-rectangle. And then as we get more and more of these, we do a better job of approximating the quantity that we're trying to calculate. And eventually we get to the actual limit, which is the integrals themselves. So we're going to do the same thing but we're going to use polar rectangles this time. So maybe, let's say we have some angles here. Maybe something like this. I'm going to try my best to draw really nice arcs here. So maybe something like this. So here is the region R, this solid here. And we have that theta is equal to some alpha. And then we have that theta is equal to some beta. We also have that R is equal to some A and R is equal to some B. So now we're going to try to subdivide this. So first, let's do R. So maybe we do something like this. So now we've broken up R into 4 subintervals. And then maybe we do the same thing with theta. So maybe we do something like here. And then we could do something like this. And we can do even one kind of just down the middle right there. So now we have 4 subintervals in both of these directions, right? Theta has 4 subintervals and R has 4 subintervals. So these are subrectangles in the sense, right? These are just polar rectangles. Then each subrectangle we'll call Rij. Are all of the ordered pairs R and theta such that the radius is bounded between Ri minus 1 and Ri, and theta is bounded by theta j minus 1 and theta j. So maybe we have, however we kind of denote our indexing here. But each one of these is going to be some sub-rectangle. What we're going to do is each of these sub-rectangles has a center that we'll call all Rij star, which is 1/2 Ri minus 1 plus Ri, and a theta ij star that is a 1/2 theta j minus 1 plus theta j. So on each of these subintervals, we're going halfway in theta. So maybe we go halfway for this particular, and then halfway in R. So maybe we're about somewhere right here. And that's going to be our sampling point. So now since the area of a sector of a circle is 1/2 r squared times theta the area of each subrectangle Rij is, again, we'll call this delta A ij, and it is 1/2 Ri squared times delta theta j minus 1/2 Ri minus 1 squared, and the change in theta j. Right, because this is adding up the area of the circle, or the sector of the circle that starts at the origin. So maybe on this particular one, we get this area here, but then we want to subtract the area from here. That way we generate only the area in this little subrectangle. So now let's kind of massage this a little bit. Let's see what we can make this into. Well, we can say that this is 1/2 Ri plus Ri minus 1 times Ri minus Ri minus 1 times the change in theta j, right? This is like a perfect square, so we can unfoil it this way. Just kind of factor it into these pieces. But notice here that one of these is by definition what the Ri star, Rij star, right? It's this term right here. And this is just the change in R. So we can again change this a little bit and write this as Rij star times the change in R and the change in theta. So this is our small area component. And we can write it as a small change in R, a small change in theta, but now we've got this extra sampling point that's kind of floating here. So let's kind of write this as a Riemann sum. So thus, the Riemann sum is our first sum goes from I equals 1 to some m, and maybe we have some other sum here that goes from j equals 1 to some n, and we have f of x and y, but we can't use x and y. But what we can do is convert each one of those to its polar coordinate form. So we can say Rij star and times cosine of theta ij star, comma, so this is our x component. And then here we have Rij star sine of theta ij star. So that ends our f of x and y. And now we have to multiply this by this delta area. So you have to multiply it by this little area right here, because then we have this height times some area that will generate some volume. So we multiply by our form here, So just put a dot here. It's times Rij star times the change in the radius, and then the change in the angle theta. So now the idea here is this is a good approximation. We increase m and n, we make these sub-rectangles smaller and smaller and smaller. We're getting a better and better approximation. And in the limit, as we let that delta Ri and delta theta j go to 0, we have an infinite number of these subrectangles, and we can generate the actual answer. These sums then become integrals. So then the limit, so in the limit, where both of these are going to 0, we get that the double integral over the region R of f of x and y dA is the integral from alpha to beta, the integral from a to b of f of r cosine theta, comma, r sine theta, r dr d theta. So there's a few things that we can note here, right? We started with this integral that has f of x and y. It's over some generic region R that perhaps we can write in polar coordinates relatively easy. In fact, a polar rectangle. We can write this as the integral from alpha to beta. This is the angle. And then the integral from a to b for r. And then we convert all of the x's that were in f to r cosine thetas. And anytime we see a y, we translate this to r sine of theta. There's a big difference here. We've got this term that just kind of showed up. This r that's just floating here, right? It's just some extra r, and that came from this r right here that came from our area term, right? Our area term had this extra r that was just kind of floating there. So the reason why I'm kind of pointing it out is because I do not want you to forget this. Do not forget that r. That r is supposed to be here. This is very important. So if you want to convert to polar coordinates and you do this double integral, you're going to have this extra r into your integrand. So now, oh, we called this r. Now, if the region R is some domain that is not a polar rectangle, perhaps like the region that we can define, so maybe we call this region D, and it's equal to the set of all points that are r and theta, such that theta is bound between alpha and beta, and then r is bounded by functions of theta. So this is very similar to what we discussed yesterday, right? So if we have a generic region, it's not a rectangle, but one of the variables can be bounded by functions of the other, then we can write this pretty nicely. We can say that the double integral over the region D of f of x and y dA is the integral from alpha to beta, and then the integral from h1 of theta to h2 of theta, f of r cosine theta, r sine theta, r dr d theta. So just like before, we have to make sure we do the right orientation for our integrals. Here we're doing r first, so we get rid of all of the r's in our expression and then replace them with functions of theta. And then we integrate with respect to theta, so we'll integrate out all the thetas and replace them with constants. So at the end of the day, we have just a constant left. So this is pretty similar to Cartesian. So most of the time, I think you want to describe your region with the bounds being on R that are functions of theta. Now, it is true that you could do this the other way. You could have perhaps maybe a region that's best described by where R is a constant, but theta is a function of R. Doesn't come up that often, but it's definitely something to keep in mind. But most of the time, I think you'll see it in this kind of way, where R is now bounded by functions of theta. But keep in mind, you could do it the other way for certain regions. So let's do an example. Let's evaluate the double integral over the region D of x squared plus y squared dA, where D is the quarter circle of radius 1 in the first quadrant. Okay, so first thing we're going to do, let's sketch what our region looks like. So if I'm only in the first quadrant, I can do something like this. And we have the quarter circle, that's of radius 1. That's kind of fixed here. So maybe it looks something like this. And this will be our region D. We go from 0 to 1 and 0 to 1. And this is in fact x squared plus y squared is equal to 1, this curve here. So we could try to do this in Cartesian. Let's see what happens if we do this in Cartesian. This in Cartesian. One way to write this, we would have to write the double integrals out, and then we would have the integrand x squared plus y squared. And then I'm going to do dy dx first, which means I'm going from bounds of x, right? So I'm going up along vertically. So I go from y equals 0 all the way up to this line, which I can solve for as a function of x. So this goes from 0 to the square root of 1 minus x squared. And then all of these traces in the x direction go from 0 to 1. So I could do this. This is the setup for Cartesian. That doesn't look great. I think this is actually going to be pretty hard with these radicals, right? We would do this y integral. This would become a y cubed over 3. We'd get a y here, and then we replace all these y's with all these radicals. And then we would probably have to do like a trig sub, and we could do it. Could certainly do it. But this is a really nice region described by polar coordinates. So in polar coordinates, one thing to also note is that this integrand, x squared plus y squared, is equal to r squared. That's pretty nice. So we can start setting up our integral. So we have two integrals here. We've changed the integrand to being r squared. I have my dr d theta, and I can't forget this extra r that comes in. So this is what our integrand can look like. I'm just doing dr d theta. This is a polar rectangle, so we could do it the reverse order, but I just chose dr d theta. So we have that r goes out from 0 to 1, and we have d theta go from 0 to pi over 2. This looks a lot easier to integrate. So let's go ahead. So the integral from 0 to pi over 2. We had an r cubed here. So what we'll get is a r to the 4th over 4 evaluated at r equals 0 and r equals 1 d theta, or this is the integral from 0 to pi over 2, 1/4 d theta. And now this is just one-fourth times theta. Theta from 0 to theta is pi over 2, or pi over 8. So this was a lot easier for us to do than trying to do this Cartesian setup. Right? This was just a really easy r cubed. Right? Theta didn't even show up in here. Okay, so let's do another example. Let's step it up a little bit. We're going to find the double integral over the region D of e to the x squared plus y squared, all in the exponent, dA, where D is the semicircle bounded by y is equal to the square root of 1 minus x squared. And the x-axis. All right, first things first. Let's plot our region. So I look at this here, and I know that this is a circle of radius 1 centered at the origin. So what we could do is we can square both sides. This is y squared is equal to a 1 minus x squared, or this is y squared plus x squared is equal to 1. Right? So there's that, the circle of radius 1. But because we have it in this form, this only is the top of the circle, right? Because in the reverse order, when we take the square root of this y squared, we get plus or minus, and we don't have the minus here. This is just the plus. So this is the top of the circle. So something like maybe like that. And then we're also bounded by the x-axis. So we have our region D here. Because it's of radius 1, I know this goes from -1 to 1, as well as from 0 to 1 here. And we can write this as y is equal to the square root of 1 minus x squared. Okay, so obviously this is the polar section, so we're going to do this in polar coordinates, but it's more than just that this is a nice domain. In fact, in Cartesian coordinates, our integrand e to the x squared plus y squared does not have an elementary integral. We couldn't do it. We could set it up, but given what we know at this point, there's no way for us to do it in Cartesian coordinates. The way to do something like this, if it's not in a good domain, is you would need complex analysis. You have to bring this thing into the complex plane and do a bunch of crazy stuff. But because this is a nice region, let's try this in polar coordinates and see if we can get away with it. So let's try in polar. The double integral over this region D of e to the x squared plus y squared dA is, this again is a polar rectangle, but let's wait to do the bounds. Let's do our integrand first. So here, this x squared plus y squared gives me an r squared. I'm going to do dr d theta. This is a polar rectangle, so I don't really have to worry about the order too much. And then here, I have to remember my extra r. So let's look at the bounds now. R goes from 0 to 1. This is a circle with radius 1. And theta goes from 0 to pi. Okay, perfect. In fact, this r is so helpful. If this r wasn't here, we wouldn't be able to integrate this using techniques that we know. So let's go ahead. Because this r is here, this is actually a u substitution. So we can let r squared equal u. So then we have that du is equal to 2r dr, which means that this r dr, the thing that I have right here, is equal to 1/2 du. So my integral, maybe we call this I is equal to, so theta remains the same, 0 to pi, and then I have some integrand or some integral here. I have e to the u. I changed r dr into 1/2 du. I still have my d theta, but now I have to think about these bounds. So I have to look back at my relationship here to come up with the new bounds in this u space. When r is 0, so you plug in 0, I get that u is equal to 0. When r is 1, u is equal to 1. Funny enough, it's the same bounds. But we did have to think about, we had to do this translation. So now this is the integral to solve. We can actually do this. So this is equal to the integral from 0 to pi. And then we integrate with respect to u. So we get 1/2 e to the u. U is equal to 0. U is equal to 1. D theta. Or this is the integral from 0 to pi. Oh, lost myself in my notes. Okay, here we go. Yeah, 1/2 e to the 1 minus e to the 0, which is just 1, d theta. And we're almost done here. So then we can just integrate this guy. So notice there's no thetas here. So this will just be multiplied by theta, and we're evaluating at 0 and pi. So this ends up just becoming pi over 2 e minus 1. Pretty cool, right? We had this integral in Cartesian coordinates that the integrand was so gross that we could set it up and then couldn't even perform it, right? But in polar coordinates, we get this extra r here, and it allows us to do the problem. So sometimes it might be really crazy for us to kind of try to take this route in Cartesian coordinates, or vice versa. Maybe the coordinate system that you're in doesn't allow you to find this elementary integrand, or sorry, elementary antiderivative. So perhaps changing coordinate systems will help us. Okay, so with that, we're at 1:30. So why don't we take just a little break? We kind of went over, and I want you guys to be able to get to your recitation.